for the data processing working group session. Professor Antoine Petiteau from Paris Diderot University, and Dr. John Baker from NASA Goddard Space Flight Center. So Professor Petiteau works on LISA as well as pulsar timing array related science. He's a French PI of the LISA Pathfinder mission, French scientific lead of the LISA Data Processing Center, co-chair of the Data Processing Working Group, and co-PI of the LISA mission. Dr. Baker is a theoretical astrophysicist. His work includes the modeling and parameter estimation aspects of LISA sources, as well as the mock LISA data challenges. He's also a co-PI of the working group. Yeah, Antoine and John, please take it away.
Okay, thank you very much for the invitation. Is the sound okay? Sorry?
Yeah.
Okay. So thank you very much for inviting us to this workshop. We will present the LISA data processing group, which is one of the three main groups of the LISA consortium. Can you see the new slide, or because sometimes it's stuck?
Yes.
Okay. So here is the usual picture that you already saw about the sensitivity of LISA. And we can see the different sources that we are trying to observe with LISA. You have the galactic binary, the verification binary, the supermassive black hole here, and the galactic background, the MRI, and the stellar mass black hole binary on the left, on the right. So this picture is to show the diversity of sources that we have to analyze with LISA, and the complexity of the LISA data analysis challenge. Here is so the source are emitting between 0.02 millihertz and 1 hertz, and we have something like 25 to extract 25,000 galactic binary, 10 to 100 supermassive black hole binary per year, 1,000 MRI per year. Basically, we don't know the rate. The stellar mass black hole binary, and also the cosmological background. In this picture, I showed just an example, just mixing the galactic binary and the supermassive black hole. And here it's a time series corresponding to this picture, and we see it gives an example of the type of data that we have to analyze. The LISA data. So we have this gravitational wave source emitting the gravitational wave, and we have our mission that is a survey type observatory. This mission will produce the main scientific data, phase meter data, but we will also have gravitational reference sensor information and auxiliary channel. And all this data will be received at the Mission Operation Center at ESOC, for example, in Darmstadt. And then we will have to process this data. So doing some calibration, doing some resynchronization of the clock, time delay interferometry to reduce the laser noise. And we will produce what we call the 3 TDI channel with mainly 2 independent channel plus a null channel. And from this TDI channel, we have to extract the gravitational wave information. So doing the big processing, the big data analysis to produce the catalog of source with their waveform. We have some denomination, some naming for the data level. So the raw data are it's what we call the L0 data. The TDI data are the L1 data. The L2 data is the result of multiple pipeline that will produce a preliminary catalog, let's say, and the final catalog are called the L3 data. Here's the organization of the LISA ground segment. We have in blue what concern ESA, and in red what concern the consortium. So you have the Mission Operation Center at ESA that will receive the data and communicate with the spacecraft, then provide to the Science Operations Center this L0 data. Then the SOC will perform some first reduction of the noise, suppression of the laser noise in particular, monitoring of the instrument, the subsystem, etc. And the consortium will help the SOC in this activity because we have experts of the instrument in the consortium via the SOC support. When this is done, we have the L1 data, and then the consortium will process this L1 data via the distributed data processing center that will produce the L2 and the L3. And it's these two parts, the two red box, are grouped in what we call the LISA data processing group. And what we call the science ground segment is the SOC plus the consortium contribution here. And the consortium will contribute, will communicate, of course, with the consortium member to analyze the data. And ESA is responsible of producing the final product, the event notice for the alert, for example. So what is the particularity of the LISA data? It's the first time that we are doing this kind of data analysis, that we have this kind of data, and there's potential unknown sources. We need to keep flexibility, continuous evolution, and we will have fluctuation of the computational charge. We are expecting that. In terms of, so here it's another vision of this data flow. So from the L0, the noise reduction, we have what we call the noise reduction pipeline to produce the L1 data. And then we have the extraction of the source via multiple pipeline to produce the general product. Of course, the picture is more complicated. And here I'm showing an example of a different schema possible. But here I'm just showing an example of. And in this example, we are first calibrating the data, then doing some clock synchronization, so having all the data on the same time grid, then doing some first TBI correction, so basically to remove the spacecraft jitter. So we are back to test mass measurement if you want. Then we remove part of the laser noise, then a second TDI that remove another part of the laser noise. So we have after this stage, all the laser noise are reduced below the level that we want. Then we have the clock jitter correction and maybe some possible TTL correction. In terms of L1, L2, it's we are just starting. We did several LISA data challenge, but we are already starting to see to have a global picture. But the two main components will be the low latency pipeline to issue the alerts, and the deep analysis that will do the full investigation to extract as much as we can in terms of science. In terms of timeline, so you probably saw this timeline yesterday, but we are in phase A until 2022, and then we will have the phase B1 until adoption. Sorry, I shift. The adoption should be after the phase B1, and then we have the launch that is here, the big L. So around 2034. Then 1.5 years of transfer, 9 months of commissioning, and then the scientific operation. And so we have different time schedule for this activity. We have the short-term activity that are the one that we are doing for the phase A, the long-term activity that are basically until the operation and then the operation. And during this phase A, so the short-term activity, we need to define the scope. We need the definition of what we want to do, the scope, define the scope, and try to have a first organization. I already said that it's the first mission of this kind, but so we need to, as soon as possible, start to prototype, develop some method, some data analysis in order to be ready on time. And we also need to support the activity of the consortium by what we call, for example, the figure of merit, the performance model, and the simulation. in terms of organization, the LDPG is now part of the formulation activity in the consortium. This formulation activity that are organized by what we call the formulation team. So it's this box here, but it has strong relation with the LISA science group that is defining basically the logic of the pipeline for extracting gravitational source and the final product that we want to produce too. So in terms of this formulation activity, for some activity, we are working with the formulation management team, and some other activity are fully delegated to the LDPG. So in the LISA data processing group, we are organized in multiple working groups. I will not, so they are listed here. I will not go in order in terms of number, but more in terms of logic. First, I will present the logic for the prototyping and the data analysis. So first we need some data to test, to play with, to see if everything is fine. So it's the simulation working group, the working group 7. And here we are talking about instrument simulation. We have now the simulator that we are using now in the consortium is called LISA Node, and it's the core. It's a core instrument simulator. It's a time domain simulator in C++ Python, and it simulates the instrument. So the noise source, the beam propagation, and the onboard processing. It can also include a part of the processing that we will do on ground, the in-rep part. And we have a constant increase of realism in this simulator. We have external module for this simulator for generating orbits, frequency plan, glitches. And we also have other simulator that are complementary to LISA node. A simulator, for example, for the 3D dynamic of the spacecraft with the test mass, trying to take into account all the control loop with the DFACS, the drag-free and attitude control system. LISA instrument, that is a fast version of LISA node. Simscape simulator, developed by Martin Whitson, that is a thermomechanical simulator, but also including some electronic and some, for example, some optic simulator. I'm not listing everything here, it's just to give you an idea. Then we need to process, so we simulate the L0 data at this level. So now we need to process them. So it's the initial noise reduction pipeline to generate the L1 data, the TDI data. The idea of INREP is it's mainly developed by the consortium, but it will be operated by ESA. The core activity of this of INREP are, okay, at the moment, we are working on specification and interface. We are also working on the prototyping, what we call the reference implementation, and also on transfer function, so analytical modeling of the TDI, the propagation of the noise through TDI, and we are validating this transfer function via simulation. Here it's an example. INREP is part of the L0 and to L1 processing, but it's not the full L0 to L1 processing. There are other things. So INREP is here, but you also have the monitoring of the subsystem, the instrument monitoring and noise characterization that will come, and part, or at least part of the L0 data will also be included in the L1 to allow to maximize the number of possibility during the gravitational wave extraction. What I mean by that is when we want to extract gravitational waves, there are some possible correlation with the various noise or possible artifact. So it's possible to have to directly process the L0 data instead of the L1 data if needed. The majority of the pipeline are working with the TDI data where the noise are already reduced, but we want to leave this possibility if needed. Then the prototyping activity that is mainly based on the LISA data challenge. And I think there is a talk just after on the LISA data challenge, so I will not talk too much about that. Just in short, we have the LDC1A simple source that has been already done. We are in process of analyzing the LDC2A, and the LDC2B and 1B are in preparation. And what is the very important outcome of the LDC in terms of for the LDPG is it will help us to estimate the resource that we need. So to give you the global picture, so we have the simulation part and then the science ground segment processing. And we are organized, here it's a more detailed organization of how we are doing all this flow that I presented with the 3 working group, but not only these 3 working group, we also have interaction, all the pink violet boxes correspond to the LSG. Here we have astrophysical population from the LSG, cosmological prediction. Then we have the source maker that is developed by the LDPG. The waveform are developed by the LSG. I already talked about the simulation, the project, the orbits. The in-rep is done by the LDPG, but for example, in terms of data analysis, it's a mix of between LDPG and LSG. So it's why I say that we are interacting a lot with the LSG. Then the working group 4, the other working group that we have in the LDPG. Working group 4 is about tool, method, product assurance, quality assurance. So we are developing in this group a common development reference environment. So it's to have a common basis for all the code in the consortium. They also develop some processes for software release, for documentation. We are working on Jira Confluence, and they also develop, and it's mainly a task done by ESA, a parameter database that will contain all the parameters of the mission. Then the group support is helping in terms of infrastructure. So for example, all this global scheme that I saw in the previous graph about the LDC processing is done by this support group. The figure of merit that infrastructure is done by this group, implementation of the performance tool, etc. And then the last group, it's more for a long-term activity. It's the design of the future distributed data processing. So the current activity are on the data analysis logic concept, the architecture concept challenges, the data model basis, and the operation concept. I will let John now present this slide and give you some input about the possible contribution.
Yeah, hi. So this is what Antoine's been talking about what the picture of our activities look like now. But if we look forward in the future, thinking about how the ground segment is going to operate during the actual science operations, it may be, it's a little bit different picture. We're planning for that now, but it's not exactly the same kind of activity. So this is just really a very sketchy slide here to give a kind of just to open up to ideas about thinking about how might Canada fit into the science operations for the mission. And there's a number of different possibilities. Actually, I started this slide from a similar slide that we had at NASA, thinking about the different ways in which NASA interacts with the project. So the core, sort of first basic way of interaction is just right through being members of the consortium, and that can happen at individual group levels, or there can be sort of large scale commitments, that are kind of national level efforts. And at some point, especially those big national level efforts are something that the whole consortium and the whole community of including ESA and international partners that are going to be working together on this have to come to an agreement as to who's doing what in the mission. And that's actually relatively soon. Antoine showed the milestone there of what's called mission adoption, and that's sort of planned for 2024. So we'd like to sort of have at least a sort of first draft of how we're going to work together and be able to have different countries sign up for what their role is going to be. And that primarily includes the contributions to the hardware, but also contributions to the ground segment are important. And so we envision right now that the LISA data processing center is a distributed data processing center. And so there will be components that may be in different countries. And so one possibility is that there could be a data processing center for LISA that's sited in Canada, and where Canadian researchers can kind of be directly contributing to that part of the ground segment processing. So yeah, of course, if the commitment is not as formal, there's always the option of having Canadian researchers just work with the publicly released data as sort of external participants in the science analysis. Exactly what the boundaries are between the sort of consortium science that will be involved in, presumably, and we're planning several key science investigations that address the science requirements concepts for the mission. But exactly how much work gets done by the consortium and how much is left to the community to do is still something that we're working on. Of course, the downside of this is that you're really getting into the game late if that's the primary way you're looking at it. And then I just mentioned another one here, and I don't really understand the geopolitical relations here. I know that Canada is kind of a sort of quasi-associated to the European Space Agency. So is it like a regular European country that participates in the consortium in the usual way, or does it have another kind of relationship with ESA, and might there be Canadian contributions that are more directed on the ESA side of things? NASA has that kind of contribution as well. I don't know what makes sense for Canada, but just a little stimulation there. Antoine, do you want to do the last slide, or?
No, I think we are okay. We can take question now.
Okay.
Okay. Thank you, Antoine and John, for the very nice talk. So we do have questions in the chat. I think the first one is from Louis. He's asking about, I think probably John, you partially answered that, but I think it makes sense to read it again. So according to your expectations of the number of events per year, and given their durations, how many events are expected to overlap in, let's say, 1 second of data?
But John, since you started, I let you.
Sure. Can you put it on your slide that had the pictures of the data in the beginning? Yeah. So you can see this. So I answered in the chat, but the short answer is in any second there should be something like 20,000 individually detectable sources that are overlapping in there. Of course, we're not going to be able to use 1 second of data to individually detect those, but those persist over the course of the mission. So their data is in every part there, and those sources are these 25,000 galactic binaries. And so, in fact, many of those, there'll be so many of those that we won't be able to individually detect them all. At some point, they add together as a kind of a noise confusion at the lower parts of LISA's band. There's also these sources that are more event-like. You see these traces in the time frequency plot above. Those are black hole merger signals. They start out not changing very at lower frequencies, not changing very fast over potentially sort of longest times. They could last for a year or more, but mostly these would be on the order of days or weeks. And then they're very loud at the end, strong signals that have signal to noise of as much as 1,000 or something. And so other sources, MREs, are maybe a little bit like those massive black holes in being more event-like, but they stellar scale black hole binaries are somewhere in between the galactic binaries and these black hole mergers. We don't see the merger of those in LISA's band, but they start out looking similar to the galactic binaries with a fairly slow chirp rate and may last years, and then they can sweep. This is down at the bottom on the right hand side there. They start out here, may spend a long time in Lisa's band there at around 10 millihertz, tens of millihertz. And they may never reach out of Lisa's band, but some of them will sweep all the way across, and shortly before, maybe weeks before, they would be detectable by ground-based detectors. So that's a long answer.
Okay, we have another question from Scott. Do you have a sense of the magnitude of computing resources needed for a possible LISA data computing center in Canada?
Antoine, you want to do that one?
It's not so. What we know that we need probably several thousand of core running at the same time to analyze the data, and after it's hard to, according to some scientists working on the LDC, as much as you have, as much as you can do, but I think typically several thousand of core at the same time is a typical time scale. It's a typical scale, and so at the moment we are in a very early stage, so it's too early to say that this country will do exactly this number of this part of the computing, etc. But typically, it's the size of the center that we are taking into account. Something like 100, 2,000 CPU devoted to the mission. Maybe John, you can complete the answer. But we are really in a process of doing the LDC in order to have a better estimation of this kind of number and to have the correct scaling.
Yeah, I'll just add to that. Yeah, the LDC is specifically kind of trying to make an early estimate of this, but because, as Antoine emphasized, it's a new kind of mission, a new kind of data. We haven't ever observed gravitational waves in this band before, so nor have we operated this kind of instrument. So we don't know exactly how much work it's going to take, and we don't know exactly which methods are going to be the most efficient methods to pursue it. So, we have sort of our current estimates, but the developments of this is a hot research area that Canadians can of course join in and try to figure out how can we make the computational problems here more manageable, and gain the best insight from the data.
Okay. I think we have another question by David. Are there large-scale international data processing collaboration already in place in which Canada makes considerable contribution, like in particle physics, astronomy? Would there be act as example what or what not to do? I guess this question is probably partially answered in the chat as well. But Antoine and John.
Yes, but we are looking at this kind of collaboration, and yes, we are looking at the different model that have been used, but also mainly in space mission. For example, in Gaia, they use a particular way of organizing the computing, or in Euclid, another European mission. So. And also, yes, in particle physics, for example, one of the computing center that we're using at the moment is one computing center in France called CCN2P3. That is one of the big center for the Atlas CERN. So yes, we are looking at all these things, and it's a way of we can have a similar scheme. John, if you want to complete.
No, yeah, we're looking for working together in lots of different ways. So a major computational contribution would certainly be something interesting.
Yeah, and I saw the comment on SK. We are not this. SK is a very, very large computation. We are not. Hopefully, we are not at the level of SK, but so we don't need a dedicated. We are not necessarily planning only dedicated infrastructure. Maybe some shared infrastructure could be envisaged.
Okay, thank you, Antoine and John. I think this is time for the next session. So
thank you very much.
Yeah, for
Thank
those
you.
questions not discussed, please put them in the Slack channel. So